Look how big that quadratic equation is. Oh my goodness. So many k's. This will be fun. So here we have a quadratic equation, right? And we need to show that the roots, right, the solution, the x-intercept, the roots of the equation can never be equal. That just means they can't be the same. So graphically, roots are the same if there's one intercept, right, like that, and it's repeated. And we know using the discriminant, that happens when the discriminant is equal to 0. So we need to show that the discriminant of this quadratic equation cannot be equal to 0. Because if it can be equal to 0, that means it is possible for there to be two identical roots. But we need to show that they can never be the same, right? They can never be equal to each other. So to get started, let's find the discriminant. So A is 1, B is 2 bracket k plus 1, and C is minus k squared plus 2k plus 5. So discriminant equals b squared minus 4ac. So b is 2 bracket, let me just expand it out first, so 2k plus 2, right? So I just distributed the 2. That's squared, so b squared minus 4 times a, which is 1, times c, which is minus, oh, need to be careful here, which is minus bracket k squared plus 2k plus 5 bracket. Lots of brackets, right? But we don't want that minus sign to stuff us up, so it's worth it. I like to think of brackets as my layers of protection against the negative signs, but then too many, and you know. Anyway, so let's simplify this a bit. So we can expand this first term out to 4k squared. If you're not comfortable expanding this out straight away, you could write it twice like this. So maybe I'll do that. And then here we have minus 4. The 1 basically just goes away, right? Minus 4 times a negative sign will become positive 4. And we're left with k squared plus 2k plus 5. Now we can expand these double brackets out. 4k squared plus 4k, like a 4k TV, plus 4k, lots of 4s, plus 4, oh my goodness, so many 4s, plus another 4. Are you for real? 4k squared, oh thankfully, and 8k plus 20. Now let's group like terms. 4k squared, 8k squared, 4k, 8k, 16k, 4, 24. So the discriminant of this quadratic equation is itself a quadratic in terms of k, right? Remember, k is just a number, k is a constant. Can we simplify this anymore? Well, we said the discriminant must equal 0, right, for there to be two equal roots, and we're showing that that's not true, so let's set it equal to 0, and we could divide everything by 8, right? I see a common factor of 8. That'll just make it a bit simpler. And remember, we set the discriminant equal to 0 for there to be two identical roots. Now we need to ask the question, okay, is it possible for there to be a value of k so that k squared plus 2k plus 3 does equal 0? Because if there is, it means this original quadratic, right at the top, could have a value of k so that the discriminant is equal to 0, which means there would be two identical roots. So what we need to do here, it's quite trippy. We take the discriminant of the discriminant, right? And why we're doing that is we want to show that there is no values of k for this to be true, right? And using the discriminant, we can hopefully show that it is a negative number, which means there's no solutions for this quadratic, which means this quadratic cannot have identical roots. So let's call that first one discriminant 1. Now we need discriminant 2 to be negative, right? Where discriminant 2 is b squared minus 4ac of this quadratic. So b is 2, minus 4 times a is 1, times c is positive 3, which is 4 minus 12, which is minus 8. So we've shown discriminant 2, which is minus 8, is less than 0. Therefore, discriminant 1, this one here, has no real solutions. Or, yeah, has no real solutions. Hence, the original quadratic equation cannot have two identical roots. And then we're done. Yep, I know, a bit Inception-like, discriminant within a discriminant. But to summarize this one, we have a quadratic with some unknown constant in it. We found the discriminant, and we want to show that the roots can never be the same, which means the discriminant cannot be equal to 0. Okay, and we set it equal to 0, and then showed that there's actually no solutions for that. So we showed that discriminant 1 cannot be equal to 0 for any value of k. All right, good job. Keep it up. See you next time.